Hi, we are going to explain the detailed steps of implementing the project number 4. This is about the file system. There are basically 3 things in project number 4. We are going to implement the buffer cache in the Pintos file system. And then we are going to extend the Pintos file system such that the individual files are represented by the set of blocks indexed and make it extensible. And then we are going to implement the subdirectories. Before we move on, we're gonna explain a few basic concepts in the file system. One of the most important data structure in the file system is inode. Inode represent a file on the disk. So every file has its own inode. It's a data structure. And what does it represent? It contains a size of the file, how large is the file, and it contains the location of data blocks that belongs to a file. So it may be a pointer to the disk blocks that belongs to a file. And also, it contains a permission and the time it has been accessed for the last time, and then the most recent modification time, and etc. etc. There are 2 types of inode. There are on-disk inode and in-memory inode. So on the disk, there are an array of inodes that each of the inode represent the files on the disk. When the operating system wants to access a file on the disk, it has to read the inode from the disk, and based upon the disk-based inode, it builds a in-memory inode. So in-memory inode is a superset of on-disk inode. So this is on-disk inode, and in-memory inode or in-core inode represent a data structure that contains on-disk inode and some other informations. The other informations include the disk location of the on-disk inode, and also it may contains the file system that the inode belongs. Another important data structure is a file object. So there is inode object, and there is a file object. File object represent an open file. In Unix, when a file is opened, the operating system defines a current offset. This is one of the most important concepts in modern file system. Current offset denotes the position within a file where the read or write system course has to be applied. For example, here, this is big file, and this is start of the file, and this is the end of the file. And then Unix operating system defines an attribute called current offset, which represents a location where the read or write operation has to be applied. Once the read or write system core is applied, then offset is updated by the amount of data that has been read or that has been written to based upon the read-write system core. So it is updated. Okay, so there are 2 concepts, inode and file object. Before we move on, let me introduce another basic concepts. There are a file. This is just a regular file, and this is directory, and this is bitmap. So each file has actual data. This is the data blocks. It may be music file, it may be video file, may be Microsoft Word file, or it may be a C code. Anyway, it may contain the music contents, video imageries, or documents, or C files. And then this is the actual contents of the file. However, every file has its associated inode. And inode contains, as I told you before, it contains a size, it contains permission, and each inode contains a pointer to the data blocks which it holds. Okay? So this is how regular file is represented. In this form, the file, the block of a file is represented by the start address and the start address. Sorry, this should be size. My apologies. So at the beginning of the file, this is start address. And this is size. So in this type of representation, okay, data that belongs to a file is represented by the start address on the disk and the size of the data that it occupies on the disk. So it may, if it occupies 3 megabytes, then file size is going to be 3 megabyte. If it's a big movie file, and then the size of the file corresponds to 1 gigabyte, then this file occupies consecutive 1 gigabytes of the data blocks consecutively. That is very important. So this is how Pintos represent a file. This is current form. And the second thing is directory. Directory is a set of files. Okay, so I guess all of you are very familiar with the term directory, except that what you are probably don't know the exact definition of the directory. Directory is a set of file name and inode number pair. So directory is file name and inode number pair. And this is a definition of directory. But in Pintos, directory itself is also a file. That is standard way of representing a directory in Unix file system. So same as in Unix, Pintos defines a directory as a file. It means that directory has its own inode. And then inode has a pointer to the data block location. Different from the regular file, directory file contains an array of file name and inode pair. And each pair is represented by file name and inode number. And each entry is called entry in the directory, which is called directory entry. The third concept you might want to know is a bitmap. Bitmap is array of bits. It's very easy. So 0, 0, 1, 0, 0, 1, 0, 0, something, something. This is bitmap. We're going to explain why and how bitmap is applied in Pintos operating system. Anyway, in Pintos, bitmap is also represented as a file. So represented as a file, it means that bitmap has its own inode, and inode has a location or contains a location of the bitmap. Okay, so that's very coarse explanation on the basic concepts of Pintos operating system and Pintos file system. Let's move on. This is file system layout in Pintos. Let's consider. Currently, I guess you have defined Pintos file system with 8 megabytes file system size, 8 megabytes. It's pretty small, very, very small file system partition. And in Pintos, the block size is 5 kilobyte. So the term block in modern operating system is unit of I/O to the disk. So that's what we call the size of the block. In Pintos operating system, block size corresponds to 512 byte. These days, normally the block size is 4 kilobyte. So since the file system partition is 8 megabytes, so there are 16,000 blocks in this file system partition. And this is a total file system partition layout. So there are 16,000 blocks from block number 0 to block number 16,383. This is the last block. So every block is located by its index. Okay, so that is the basic size from block 0 to block 16,383. There are so many blocks. And then these are the details layout of the Pintos file system partition. One thing you might want to remember is in Pintos, inode disk, this is undisk inode. Undisk inode is 512 byte large. This is very big. Of course, inode contains, of course, inode does not use all its 512 bytes space. Only the fraction of 512 block is used for containing an information for the inode. Anyway, the first block contains an inode for bitmap file. I'm going to explain what the bitmap is shortly later. And the second block, which is block 1, contains an inode for the root directory. And from block 2 to block 5, it contains a block bitmap. Okay, so block 0 contains an inode for the bitmap file, and these are the actual contents of the bitmap file. So the block 0 contains an inode, and it should contain the start address of the bitmap file, like this. And block bitmap consists of 4 blocks from block 2 to block 5. And then block number 6 is contents of the directory. So it contains inode and file name pair for the files that resides in the root directory. So this is inode number and the file name. So this is the detailed structure of this part. And then there comes a bunch of data blocks. Okay, so let me explain what the bitmap is. Bitmap is an array of bits, of course, and each bit represents whether the associated block is being used or not. So there are 4 blocks, and each block has 512 bytes, and each byte is 8-bit. So we need to allocate 16,384 bits to represent whether each of the blocks in the file system partition is being used or not. So there are 16,384 blocks in this file system partition. So we need to allocate this much bit to represent whether each of the block is being used or not. So we are allocating 4 bits, 4 blocks. But if you double the file system partition from 8 megabyte, for example, to 32 megabyte, If we increase the file system partition size from 8 megabytes to 32 megabytes, then of course we have to allocate 16 blocks for the bitmap, not 4, because we have to quadruple the number of blocks that has been used for block bitmap. So this is file system layout in Pintos. This is details. Okay, so the first block was the inode for the bitmap, and the second block was inode bitmap for root directory, and then this from 2 to 5 was bitmap, and this was root directory. Okay, and then there is data blocks. This is plain data blocks. Let's look at the contents of the block number 0. This is an inode block for the bitmap. And in Pintos, each file block is represented by the start address and the length. Okay, so it says that start address of its contents is block number 2, and length of the file is 2048 byte. This is unit is byte, and there comes matching number, and this is set part of this data structure design. The integer array of 125 integer is being unused in this data structure. So let's assume that this is 4 byte, and this assume that this is 4 byte, and then 125 times 4, which is 500 byte, is being unused. Right. Well, this is the design of Pintos file system, and if you have time to modify, and if you have time to make it look better, and then you are welcome to modify this file system partition, and I'm sure that you should be able to do that. Okay, and then let's look at the root directory. The start address is 6. So the data block for the root directory file starts at block number 6. And then the size of the file is 320 byte. So it fits within a block because the block size is 512 byte. And then there comes huge space of unused space. Okay, so this is the inode structure. And then let's look at the contents of a root directory. As we have covered before, directory is an array. Directory is a set of file name and inode. So file name and inode in Pintos. So in Pintos data structure, directory entry is an array of file name and inode, and the length of the file name is fixed to 14 byte at maximum. That's how the Pintos defines the file name. So in Pintos, the file name cannot exceed 14 characters. However, in modern operating system, the length of the file name is virtually infinite. You can use 100 character file name or 200 character file names. Anyway, this is how Pintos represents a directory. Okay, so from block number 7, there comes a data block. So data block means you can use the blocks that starts from the block number 7 to 16,000. You can use those blocks as an inode or the data block that belongs to an inode. In this file system layout, inode number 7, block number 7 is containing an inode block, and the name of the file, we don't know what the name of the file is, but let me get back to that point later. So anyway, the inode data block starts at 8, and the length of the file is 10,024. So the length of the file is 2 blocks, and it starts from 8. So this is the data block for a block that pointed by the inode block, which is stored at block number 7. And there's another block. A block number 10 contains an inode block, and its data block starts at 11, and it consists of 2048 bytes, which corresponds to 4 blocks. So it'll be 11, 12. If we have more space, and 13 and 14, then this file will consist of 4 blocks. Okay. And I know that is stored at block number 10 is pointing to the block number 11, and it contains an information about the file size, and the file size is 2048, like this here. Okay. And then let me get back to the root directory structure. The first entry in the root directory states that name of the file is my file, and its inode number is number 7. So it is inode number, but actually it represents the location of the associated inode. So file name is my file, and the associated inode is stored at the block number 7. The second entry is file.c, this file name, and then the inode number is 10, but it represents the location of the inode. So the inode for file.c is stored at the inode number 10. There is a very, very interesting phenomenon here. As you see, in inode, there is no file name. If you look at the inode, there is no file name field. No, and no. You know what? In modern operating system, in modern file system, file name is not the part of file attribute. So for us, human being, we recognize the file by the string, which we call file name. But from computer systems point of view, file name has nothing to do with the file itself. It's not a part of the file attribute. Directory data structure relates a character string called file name to its inode. So that's the important interesting characteristics of modern file system. Okay, so there are 2 types of inode. First one is in-memory inode, and the second one is on-disk inode. So inode represents a file on the disk. All right, so let's first look at the inode we call in-memory inode. Also sometimes it is called an in-core inode. In Pintos, the name of the data structure for in-memory inode is struct_inode. And in-memory inode contains the address of the on-disk inode on the disk. It represents a block number where inode is stored. And then it contains the disk inode. So that is it. And then it contains a flag. It contains a flag whether to delete the file or not. Okay, let's look at the actual data structure. The easiest part, the sector. This is the location of the inode on the disk. So this part is done. And the last part is the data structure for on-disk inode. So as I told you before, in-memory inode is a superset of the on-disk inode. So this is in-memory inode. This is in-memory inode or in-core inode. It harbors the on-disk inode. This is on-disk inode. And it contains a sector, which represents the location of the inode on the disk. And then it contains a flag called removed to denote whether a file has been deleted or not. Of course, the file can be deleted, but operating system does not immediately deallocate the in-memory inode when a file is deleted. Normally, operating system deallocates the in-memory inodes in asynchronous manner. So when you delete the file, operating system just marks that this data structure in-memory inode needs to be deallocated and do it later at some time. So that's what this is for. And as we covered before, some files are not writable. For example, the executable file or the files that are being loaded to disk, they shouldn't be modified while the operating system modifies it. So we propose the Pintos operating system defines a field in the in-memory inode to denote whether the file can be writable or not. So it has denied write count. The reason this is a count, not the flag, is that there are multiple processes accessing the file. In that case, the file cannot be modified until none of the processes are accessing the file. So for those reasons, the Windows file system defines a deny write count, not the denied write flag. And the last thing, there is open count. It represents a number of processes or number of open system cores that has opened a given file. So that's the structure of in-memory inode. Okay, next part is more essential data structure called on-disk inode. It represents a file on the disk. So the name of the data structure is chopped inode disk. This is very large. This is 512 byte. That's very sad. And of course, unfortunately, out of 512 byte, 500 byte is not used. Okay. This is not good. However, that's the way the Pintos defines the inode. So if you have time, then put some time on modifying this data structure and make it more efficient. Give it a try. It's very easy. Anyway, the important part is how Pintos operating system defines a file. In Pintos operating system, file system represents a file as a single block of large chunk. It is pointed by the start address and the size. This is how the Pintos file system defines a file. Okay, and this is the data structure of a directory object. Directory object is a format of data block for the directory file. So directory file has its own inode. its own inode. And inode contains a pointer to the start address of the data block and its size. And it'll contain something. So this is in-memory data structure that represent a directory block. So it contains a struct directory contains the pointer to the associated inode and the position. So position defines the next directory entry to read or write. So it represents an open directory. There are two fields, inode, the pointer to the associated in-memory inode, and then POS is a position of the next directory entry to read and write. That is directory object. And let me explain the directory entry. Directory data block consists of an array of directory entries, which I have explained before. And then each directory entry is actually file name or inode number pair. Right. So inode sector is a sector number of the associated inode. And then there comes a file name. And then that slot may not be in use. In that case, we need a flag to represent whether current slot is being used or not. So the actual data structure for directory M3 is represented by the inode sector. And the character string, the maximum number, which is 14 plus 1. And then a flag to denote whether a given directory slot is being used or not. So as you can see, directory entry, this is the data structure for directory entry. So in this case, whenever you need to find a certain inode for a given file name, every time it needs to scan the directory block to find a matching file name. Well, if there are 10 files or 15 files, linearly scanning the 10 elements or 15 elements may be reasonable. But what if a directory contains like 300,000 files in a directory? Then if it is not sorted, or if it is not organized with a certain search structure, such as radix tree, B plus tree, or red flag tree, then linearly scanning the array of 3,000 elements requires substantial amount of search. It takes very long. Okay. Anyway, in Pintos, the directory is an array of directory entries, and directory entries are not sorted at all. Okay, the next data structure is block bitmap. So block bitmap represents whether a given block in the file system partition is being used or not. The data structure name is freemap. So it is a bitmap to represent the status of the blocks in the file system partition. And the bitmap is stored as a fires, which means that it has its own inode, and it has two fields, the number of disk blocks in the entire file system as bit count and actual bit array. There is another important data structure, file struct. It is created when a file is open. Remember, for closed file, this data structure is not created. So this struct file is allocated and created when file is open. And it contains a pointer to the inode. And the most important attributes of the struct file is position. It represents the position of a file where the read and write operation should apply. And it has a field to indicate whether a file is writable or not. So in this project, we have to do basically three things. First one is implement buffer cache. And second one is make the file system file abstraction indexed and extensible, and implement the subdirectories. So for buffer cache, the purpose of buffer cache is using the part of memory as a disk. So it's the opposite concept of virtual memory. In virtual memory, we are using the part of disk as memory. We're using disk as memory. In buffer cache, it's the opposite. We are using part of memory as disk. Okay, so for buffer cache, we allocate buffer cache. We are going to allocate physical page to accommodate 64 disk blocks. And we're going to cache the data blocks to this buffer cache. When reading or write to data blocks, we are going to save it to the buffer cache. And then once we are done with accessing the block, sometimes we have to save the modified data blocks back to the disk space, or when the file system is shut down. And for the file, current Pintos represent a file as a single extent, as a single consecutive block, which contains the start address and size. So in Pintos inode, it contains two fields, the start address of a file blocks and size. But what if we want to extend the block, we want to extend the file, but the next location right next to the files is already occupied by the other files, file B, for example. Then there is no way for the Pintos file system to extend this file. Then we have to find free space, and we have to find a free space that can accommodate extended file, and then we have to migrate entire file. It will consume huge amount of time for this copy. Okay. So we're gonna implement the block pointers in an inode. There are a variety of ways to represent a file blocks that belongs to a file, but we are going to use Unix-like file structure. And then we are going to implement hierarchical namespace for a file.